So for the hackathon, I want you to go to the machine learning website and to the GitHub. So this is up here. Where's my mouse versus their mouse? Okay. Hope you can see this mouse as well. So go to the GitHub one. And you might not be that familiar with programming. So what you do is you go and open that in Colab. So now we are in Colab, and while we are talking about that, I want you to start to load that. You can just press here the Run Cell button.
Do we need GPU for that?
Yes, host. Good point. It should possibly already there. So change the runtime. What is going on here? And change it to T4 GPU. It's very important. Thank you. Whoever that was, I didn't. Okay, good. Okay. So do that. Mine is already on there for some reason. I hope yours too. If not, just puts it on there because we need a GPU for that. And that installs that. Okay. Mine is done. It's quite quick. Oh, I haven't restarted my runtime. I want to restart the session here. But we're really all on the same page. Shift return will do the same thing. That will not work. Oh, it is ready. Okay. So we want to make a high angular dark field image. You can either use a hexagonal one, or you use the one from silicon, depending on whether you're more a cubic or hexagonal person. And then we make an image from that. So I'm apparently square. Didn't change things around. So that is what we use as a potential. So all we do really is we put Gaussians wherever there are atom positions. And actually, we move them around a little bit. So there is actually a wobble here. Let's make a very dramatic wobble. This one does not wobble. Why not? Sorry. That's wobble should be over here. You're right. So things are moving around and like crazy. It just should be a little bit out of whack. So you can change it around and about as you want. So for the counts, we take a relatively high count. Then we have very little noise here. And our simulated image is the ground truth that will find the blob detection very easily, right? So we're not going to do that. We're going to put much less noise, much more noise on it. Something that's maybe a little bit too low. Okay, noisy atoms, ground truth. We know where the atoms sit. And then the blob finder still finds it. So we go build a neural network. we create the training data. So that are 10 new data, 10 new images, 20 new images that we create in the same way. So they're just all over the place with the same kind of noise, all the same. And we have them labeled, so we know where they are. And now we train that. So we shift it over to the GPUs. It takes a little while, and then it moves through it quite quickly. And then we test that. And of the 161 atoms, one of them is on the very, very corner, so I didn't find them apparently. So the unit is not doing so well. That's interesting. That is a new one. Let's do it again. Something is not quite right. So we can train the unit a little bit longer. So you can do that with more talk. Just run it. See, the unit is getting trained better. So this is a unit. So we heard already about the convolutional, deep convolutional neural network. So that are basically two, one reflected. So we are using that a lot for. Okay. Okay, this is weird that it's not doing better. And so we find our atoms. Your task is going to be to increase the noise so that you basically cannot find it anymore with the blob net, and the unit should still find that. If you go here, so your problem is counts in noise, so you can reduce it to wherever you want to. Once you have done that, so we can make our images. The threshold of the blob finder can be changed around.
What the most function? It's a binary type or what?
So that's for you to find out. It's just the difference, right? So you see the whole network here. One point I want to point out before I do anything, if you're finding these kind of examples on the web or whatever, where is that? Say import torch.nn as nn or something like that. That will not be very good on the real code. So if you want to do any kind of real code, you'll find that in all my notebooks. You want to know where the different function or classes come from so that you can find that. So there is NumPy center of mass. You have your own center of mass function, or you have set as a variable. So these kind of terms that are often used, you should not keep import directly from a package. Just import the package, and then everybody knows where it comes from if you look at your code and try to troubleshoot it. So it's much easier if you're not having that kind of part. So if refrain from what we do only for the most obvious ones. So that's only NumPy as NP, that is convention, and PyLab, PyPlot, as PLT. That is a convention. Everything else should not be used in that way. You'll find it on the internet everywhere. It's useful possibly for a simple example, but if you have your own code, you will get into trouble extremely fast. So adhere to the clean code part, and large language models learn, of course, bad behavior much faster than good behavior. So we want to know who can train the network best with the lowest counts. And that is going to be your task. You can change a lot of things around.
What parameter we can change over there?
The most obvious ones is counts here, right? So I put the ones as input in the beginning. So this one you should not change too much. You can change the counts in the beginning, and then find the threshold. You move around with this one, you can change that. And if you leave these ones correctly,
Can we perform some data elements?
you can do whatever you want to. So that's just a suggestion how you start. So and then you progress as you go along. It's a hackathon, so we'll find what you do. If you want to change, you can change the training size as well. The more training size you do, input parameters you have, the better. Say such a simple network.
But we cannot change the hierarchy of the tiny events. We cannot increase the
Try that. See whether that's better within a reasonable space. So we only have a few minutes here, so to speak. So we have something like 40 minutes. So don't go overboard with changing things. So if it is too boring to just go to something small, so it gives you a starting point. So if you did something with neural networks, just go on and change the depths till you make it sure that it's still running under Google Colab. Okay. You're not allowed to go to a supercomputer and some other GPUs. The task is to stay on that one. Okay. If you have questions, we'll have people on the chat. Say, hopefully can answer your question.
For this kind of training data, because we see that we know exactly the central mass of each atomic position.
Yes, but we are not using the first one.
Yeah. For the real data, how can you find exactly the central mass for that atomic point? For the human adaptation, or how can we do that?
If it is purely crystalline, right? So if you have a crystalline data set, you can use the crystal in the same orientation, and you can make a very fast, short unit to train it on that, and then you can go and work with a very low noise level. You can rotate it according to the Fourier transform, all right? Or you rotate your image, that's what we do, so that it is in the right orientation. Or as another ground truth, you can just clean up your data and do a blob finder, then you know that your blob finder worked very well, then you can do it from that on. But that's not...
The blob finder still apply the differential of the Gaussian over there and the central mass.
Yes, the differential of the Gaussian, no, the log of the Gaussian, so it depends on what kind of blob finder you use. And that will find the atoms if it's a good image. So if you have an image with good contrast, you can actually trust the blob finder. So you get a ground truth, you move it around some, and then you can use that as an input as well. So any of that works. Add noise, take some in, take some out, depending on what you want to see. But yeah, so okay. It's a bit beyond what we wanted to do here. We just wanted to make start with a very simple network. So we had an introduction to neural networks, and we just wanted to have everybody try it out. Who has the lowest one at this point? Lowest counts, highest noise? No? Okay. Could somebody find 90% of all atoms with the counts of less than 2,000? No.
500, but there's a precision about 80.
80%, which is still pretty good, right? So 90, okay, yeah. So
You say 1,000 for your
well, no, I mean 2,000 to find 180 atoms with 2,000 electrons is already quite remarkable, right? I mean, you don't.
My test was correct.
Huh?
I forgot the album count. I got only 16,000 points.
Oh, okay.
You mean the number of atoms you found with that?
Yeah.
Okay, at the count equal to 500, and my number of atoms found is 134.
Oh, okay. So you find a fair amount of atoms, and think about it. So you have about 10 electrons per atom, right? So the Sono is of course outrageously high. I was just trying to push people below that just to see what happens. Of course, with such a low dose, right? I mean, these are insanely low doses. If you want to do that on the microscope, you really have to get your current down. So the point is, these units are available for you. Say simple ones run quite quickly, and we just wanted to get everybody to find atoms with the neural networks, and it seems like nobody complains that they didn't find anything. So at least most of you found the atoms. So that's cool, I think. And yeah, so that's it for today.